So last time we learned the first way to store a graph, the adjacency matrix, that neat little grid of ones and zeros. It was fast, it was simple. But remember the problem we ended with? When the graph got big and mostly empty, that grid wasted a huge amount of memory. 1,000 nodes meant a million boxes, most of them just sitting there, holding zeros, doing nothing. Today, we fix exactly that. We learn the second way, the adjacency list. And for most real-world graphs, like your social network, this is actually the smarter choice. Let me show you why. Let me start with something you already do every single day. Think about the contact list in your phone. You do not store a giant table of every person on earth with a yes or no next to each one saying whether you know them. That would be madness. Instead, you just keep a small list, only the people you actually know, your contacts. The rest of the world? You simply do not write them down at all. That is the entire idea behind an adjacency list. Instead of one big grid for every possible connection, we just keep, for each node, a small list of who it is actually connected to. Nothing more. Let us make it real. Imagine our 4 friends again, 0, 1, 2, and 3. Now, instead of drawing a 4x4 grid, we do something much lighter. For each friend, we keep a little list next to their name. So friend 0 has a list, friend 1 has a list, and so on. Now suppose friend 0 is connected to friend 1 and friend 2. So next to 0, we simply write 1, 2. That is 0's list. These are the only friends 0 has. Suppose friend 1 is connected to 0 and 3. So next to 1, we write 0, 3. And we keep doing this for everyone. Notice what is happening here. We are only ever writing down the connections that actually exist. If a friend has just 2 connections, their list has just 2 entries. We are not reserving space for connections that are not there. No wasted boxes. No grid full of zeros. Now, this depends on the type of graph. In an undirected graph, like a friendship, the connection is two-way. So if 0 is connected to 1, then 1 must also know about 0. That means we add 1 to 0's list, and we also add 0 to 1's list. The same edge lives in both lists. But in a directed graph, like following someone on Instagram, the connection goes only one way. So we add it to just one list, the followers list. The other node's list stays empty. Same adjacency list, we just store the edge in one direction instead of 2. Now let us see this in Java. And do not worry, it is very clean. In Java, the most natural way to build an adjacency list is using a HashMap. Think of a HashMap as a phone book. You give it a name, and it instantly gives you back that person's information. So our key is the node, the friend. And the value is a list of that friend's connections. For each friend, the map points to their own little list of neighbors. To add a two-way connection between friend A and friend B, we do 2 small things. First, we make sure both friends have a list ready. Then, we add B into A's list, and we add A into B's list. Two-way friendship, stored in both directions. And if we want to find all the friends of a particular person, we just go to the map, look up that person, and instantly get back their entire list of connections. We do not have to scan through 1,000 boxes. We just read their list directly. Now, I have shown you this in Java. If you prefer C++, it is just as easy. Instead of a hash map, you use a vector of neighbors for each node. And if your nodes are simply numbered 0, 1, 2, 3, you can even skip the map completely and use a vector of vectors. And for those of you working in C, here it is a little different, and that is okay. C does not give us a ready-made list, so we build the lists ourselves using something called a linked list. Basically, each node points to a small chain of its neighbors. The picture in your head stays exactly the same. Every node has a little list of who it is connected to. Only the plumbing changes. Now here is the honest comparison. This is the part interviewers love to ask. With the adjacency matrix, checking, are these two specific friends connected, was instant. Just peek at one box. But it wasted memory when the graph was big and empty. With the adjacency list, we save a huge amount of memory, because we only store the connections that truly exist. This is perfect for real-world graphs, which are almost always sparse. Lots of nodes, but each one connected to only a few others.
Think about it. You might be on a platform with 1 billion users, but you personally are connected to maybe a few hundred. A list only stores those few hundred. A grid would try to store 1 billion boxes for you alone. But there is a small trade-off, naturally. If you want to check whether two specific friends are directly connected with a list, you may have to go through that friend's list one by one to find the other. With a small list, this is nothing. But it is not the instant single peek that the matrix gave you. So here is the simple rule of thumb. If your graph is small or dense, meaning most nodes are connected to most others, the adjacency matrix is great. But if your graph is large and sparse, which is most real-world graphs, the adjacency list is the smarter, lighter choice. That is why social networks, maps, and the internet almost always use adjacency lists under the hood. Let us bring it all together. An adjacency list keeps, for each node, a small list of only its actual connections. It saves a lot of memory on big, sparse graphs. In Java, it is just a map from each node to its list of neighbors. Finding all neighbors of a node is quick. And for most real problems you will ever face, this is the representation you will reach for. And that is it. You now understand both ways to store a graph, the matrix and the list. You know what each one costs, and you know when to use which. Honestly, that puts you ahead of a lot of people who only memorize one and never understand the trade-off. Next time, now that we know how to store a graph, we will finally answer the most exciting question of all. How do we explore it? How does a computer start at one node and visit every connection, step by step? That is where the two most famous graph techniques come in, BFS and DFS. And trust me, once you see them, they are going to feel surprisingly simple. So, see you there.